Hello everyone. We ended up with this problem now. So we are to simulate the solution of in determining the value of the function f of a now, considering the table as shown. Okay, so we're done with this and we now proceed with our next topic. So after discussing the Lagrange interpolation formula, we now proceed with the forward Gregory-Newton interpolation formula. Okay, so in this we have the tabular values, okay, for x and f of x. Okay, so given this, uh, we are to approximate the value of the actual function, okay, not found in the table. So these are the values found in the table. However, between x of 0 and x of 1, okay, what is the value of that function? Now, what is the value of the function uh, given that there is a value between x of 0 and x of 1? So we will approximate that value applying the forward Gregory-Newton interpolation formula. Okay, and this is the formula, okay, to approximate the value of the actual function. So we have f of x, okay, is approximated as f sub 0, okay, so which is this one, f of x of 0, no, this is f sub 0, okay, this is f sub 1. Now take note that in order for this to be equal to f sub 0, f sub 1, f sub 2, and so forth, okay, certain conditions should be satisfied. So the tabular interval value between consecutive tabular values of x must be constant. No? So it should be constant. So age, okay? So the difference between x sub 1 and x sub 0 must be the same as x sub 2 and x sub 1, must be the same as x sub 3 and x sub 2, must be the same as x sub 4 and x sub 3, and so forth. Okay? Therefore, we can let f of xo equals to f sub 0, f of x1 equal to f sub 1, and so forth. Okay, that's why we have here f sub 0. Okay, now then we have r. So what is r? So r is the difference uh, between x and x sub 0, then dividing it by h. Okay, that is x minus x sub 0 over h. Okay, so that is r. Okay, so r is a certain value of x, okay, minus x sub 0. Okay, so this is x sub 0. Then we divide it by h, which is the tabular interval value. Okay, that is constant. Where this is the formula for the tabular interval, right? So this is the successive value of x minus the preceding value of x. Okay, so we know that x sub 0, x sub 1, x sub 2, x sub 3, x sub 4, and so forth are called arguments, right? As I have discussed previously, no? So in this case, we have the successive argument minus the preceding argument. We get the tabular interval value each. So analyzing this table, no, so we reconstruct the table in such a way that, so we have here k, x sub k, x sub k plus 1, and f sub k. Okay, so this is the procedure on how to uh, approximate the value of the actual function. So let this be k, and that starts with 0, okay, followed by 1, 2, and so forth. Then we have x sub k. So for k equals 0, that is x sub 0. For k equals 1, we have x sub 1, and so forth. Then for k equals 0, that is 0 plus 1, that is x sub 1. For k equals 1, we have x sub 1 plus 1, that is x sub 2, and so forth. Then we have f sub k. Okay, so in here, from k equals 0, we have f sub 0, followed by f sub 1, f sub 2, and so forth. Okay, so f of x now becomes f of x sub k. Okay, so that's it, which is equals to f of f sub k. Now, provided that the tabular interval is constant. Okay, the tabular interval is constant. So that's it. So we can proceed. So f of x sub k is equals to f sub k. So here's now the problem. So problem solving concerning the forward Gregory-Newton interpolation formula. So suppose we are to compute the cube root of 4.4 from the following table of cube root of x. So this is cube root of x. Okay, this is x. So considering the table, we are to compute cube root of 4.4. So as you have noticed, at x equals 4.4, there's no value of cube root of x, right? So there's no cube root of 4.4 value, no? So suppose we don't have a calculator, we can able to approximate the value of cube root of 4.4 using the forward Gregory-Newton interpolation formula. So let's do it. So solution. So let's analyze first whether we can apply the forward Gregory-Newton interpolation formula or not by determining whether the tabular interval is constant or not. So in here, the tabular interval is 0.5, 0.5, 0.5, no? 0.5. Okay, so since it is constant, we can now apply the forward Gregory-Newton interpolation formula. So here's the corresponding conversion. Okay, so 4 becomes x sub 0, 1.58740 becomes f of x sub o, which is f sub o. Then x sub 1 is equals to 4.5, f of x sub 1, which is equals to f sub 1, is equals to 1.65096. Okay, and the pattern continues. So note, if the difference between any two successive tabular values of x remains constant, then the forward Gregory-Newton interpolation formula can be applied, as I have said earlier, right? So we can proceed. So given now the table, we are to reconstruct the table in such a way that we will have a column for k, a column for x sub k, a column for x sub k plus 1, and a column for f sub k. Okay, so where k is starts with 0, followed by 1 until 4. then x sub 0, x sub 1, x sub 2, and so forth, x sub 1, x sub 2, x sub 3, and so forth. Okay, so for k, we don't have x sub 5. That is not applicable. Okay, we don't have x sub 5. That's invalid. Okay, that's the limitation. Then we have f sub 4. Okay, f sub 4. So in this case, we substitute the values from the table. Okay, from the table, this is x sub 0 is 4, x sub 1 is 4.5, and so forth. No? So, and then, so this is x sub 1 from the table in the previous slide, that is 4.5. In the previous slide, x sub 2 is 5, and so forth. Okay, f sub 0, okay, from the previous slide, that is 1.58740. Okay, f sub 1 is 1.65096 from the previous table, from the previous slide, no? And so forth. So you know that. And then this is the tabular interval value, which can be determined by subtracting the preceding argument from the successive argument. That is x sub k plus 1 minus x sub k. So in this case, that is 0.5, right? So that is 0.5 x sub k plus 1 minus x sub k, that is 0.5. We have already solved for that in the previous slide, right? So this is x sub k, so this is 0.5, right? This is 0.5. Okay, or should I say this is x sub k and x sub k plus 1. If you subtract, 4.5 minus 4 is 0.5. 5 minus 4.5 is 0.5. 5.5 minus 5 is 0.5. 6 minus 5.5 is 0.5. So this is no longer applicable, okay? That is no longer applicable. That's not applicable, no? So we can proceed. So then we have here, we can now construct the forward difference table. So this is the next procedure is to construct the forward difference table. Okay, so I have already taught you on how to construct the forward difference table or the advancing difference table, right? So let's construct a forward difference table that makes use of delta uppercase, the forward difference operator or the advancing difference operator. Okay, so here's the table. So I have already taught you on how to construct this table. Okay, so I will not discuss this in detail. Now, in numerical form of the forward difference table, so these are the values, right? So we are to get delta fk, delta f sub k, okay, by formula. That is 1.65096 minus 1.58740, and we get 0.06356, right? Then this is delta f sub 0. Then we have 0.05902. How did we get? 1.70998 minus 1.65096. That is delta f sub 1. Then followed by 0.05519. That is delta f sub 2, and so forth. No? So you know the pattern. Okay. Then delta squared f sub 0. That is This is delta squared f sub 0, 0.05902 minus 0.06356. We get that, followed by, so did we get the delta squared f sub 1? So that is 0.05519 minus 0.05902. So we get negative. Last, so this is delta squared f sub 2. Okay, so delta squared f sub 2. So the second differences of f. So we have 0.05195 minus 0.05519. We get negative 0.00324. So that's it. So you know the pattern, and these are the values that will be obtained. So we're now ready to apply the forward Gregory-Newton interpolation formula. So here's the formula. Okay, so we start with f sub 0, then we multiply r and delta f sub o. No, so we have r and delta f sub o. Okay, then we add the product of r and r minus 1. Okay, then we divide it by 2 factorial. Then we multiply that by delta squared f sub 0. So there is a pattern class actually. So to determine the next term, we introduce r minus 2. Then from delta squared f sub 0, it becomes delta cube f sub 0. From 2 factorial, it becomes 3 factorial. Then the next term will be, so we will introduce r minus 3. So we have r minus 1, r minus 2, r minus 3. Then 3 factorial becomes 4 factorial. Delta cube becomes delta to the 4th. That's the pattern. Okay? So if we continue, that is r minus 1, r minus 2, r minus 3, r minus 4. Okay? R minus 4 over 5 factorial. Then delta to the 5 f sub 0 and so forth. Okay? So if we continue, that's the pattern. Now, x is 4.4. We are to determine the cube root of 4.4, right? So x now is 4.4. Okay? So now h is 0.5 as computed in the previous slide. And r is x minus x sub 0 over h. Okay? So actually, this is derived from the equation x equals x sub 0 plus rh. Okay, r is derived from x equals x sub 0 plus rh. No, so in this case, for example, if I have x, so this is x sub 0, x sub 1, x sub 2. Okay, so this is x sub 0 plus rh. Okay, so for instance, I have at r equals at r equals 0, or should I say at x equals x sub 0, that is x sub 0 equals x sub 0 plus rh, right? So we know that so what is r now if x sub 0 equals to x sub 0 plus rh? Okay, so x sub 0 minus x sub 0 is 0. So 0 equals rh, therefore r is 0. So r is 0 at x sub 0 at x equals x sub 0. Okay, r is 0. Now if if x is equals to x sub 1, okay, so that is what? So that is x sub 1 equals to x sub 0 plus RH. Okay, so x sub 1, x sub 0. So that is, if we are to compute, so what is now R? X sub 1 minus x sub 0 over H, right? So we know that what is the difference between x sub 1 and x sub 0? That is H, right? This is also H, right? The difference between x sub 1 and x sub 2, x sub 0 and x sub 1, that is H. So that is H over H. Okay, that is 1. So the answer is 1. Okay, so that is the manner on how to get R. Okay, okay, so we proceed. So that is just an example, no? So we now proceed. So we have here 4.4. So it is 4.4. So we know that from the table we have 4.0, 4.5, right? So this is x. So this is x sub 0, right? This is x sub 0. So 4.4 minus x is 4.4. X is 4.4. So the difference is between the two. The difference between the two, 4.4 minus 4. Then we divide it by h, which is 0.5. Okay, we get 0.8. R is 0.8. Okay, so that's the manner on how to find R. No? So 4.4, so we have the value of x, which is 4.4 minus 4 over 0.5, the tabular interval. Okay, so that's it. Then we have, so we can now substitute the value. So we have here 4 point f of 4.4, that is 1.58740, that is f sub o, plus 0.8, that is r, multiplied by 0.06356. Okay, then plus, so this is f sub 0, that from the previous slide in the table, no? So this is the reference, so this is the reference table. Okay, this is f sub 0, this is f sub 0, this is delta f sub 0, this is delta squared f sub 0. So we will all use all of this, delta cube f sub 0, and this is delta to the fourth f sub 0. So we will use all of those. Okay, okay, so and then we have here uh, r is 0.8. Okay, then 0.06356 delta FO. Okay, so that is delta FO. That is based from the table, no? That is 0.06356. So this is zero point 0.8 minus times 0.8 minus 1 over 2 factorial. Then delta square depth of 0. This is based from the forward difference table. No? Then we have zero point 0.8 minus 1, zero point 0.8 minus 2 over 3 factorial times delta cube f sub o based from the forward difference table. Then we have this one. Okay. So based from the forward difference table, okay, this is negative 0.0012. And nothing follows plus 0. Nothing follows because based from the table, it is only up to delta to the fourth f sub k. So in other words, delta to the fifth f sub k is 0. No? There's no difference. No? So 0. So delta to the 6, delta to the 7, all are 0. No? All are zeros. Okay. So that's it. So that's why this is 0. No? Because that is the limitation until delta to the fourth f sub 0. No? So and then our final answer now is 1.63864. Therefore, the cube root of 4.4 is approximately equal to 1.63864. Okay, that's it. And this is the lab activity, no? The 12th lab activity that you will do. Simulate the solution and finding the value of cube root of a, considering the table below using Excel, applying the forward Gregory-Newton interpolation formula such that a correct approximated value of cube root of a is obtained, where a not found in the table is any real number between x sub 0 and x sub 4. Okay, so let's analyze on how to simulate, no? Simulate this problem. So in finding the value, we are to find the value of cube root of a, no? So where a is not found in the table, no? Let's say a is 4.4. Okay, a is 4.4. That is a value of x equals to 4.4. And we are to determine the cube root of 4.4. We are to approximate, no? So we will use forward Gregory-Newton interpolation formula to do that. Okay, to obtain cube root of 4.4. How about I can change it to 5.4. So what is the approximated value? What is cube root of 5.4 using the forward Gregory-Newton interpolation formula? Okay, so that is my concern, no? So what is the answer to that? Okay, considering the table below using Excel, applying the forward Gregory-Newton interpolation formula such that the correct approximated value of cube root of a is obtained, where a is any real number. It can be decimal, it can be whole number, between x sub 0 and x sub 4, between 4 and 6. So it should only be between 4 and 6. So what is the approximated value of a? The approximated value of the function, value of cube root of a, no? Let's say 5.2. What is the approximated value of cube root of 5.2? Approximately equal to what? Applying the forward Gregory-Newton interpolation formula. Okay? So let's answer. Let me show you how to do it. I have here an example. no? So here's the so this is what you will do. So so this is the simulation of the previous problem I have shown. Okay. So this is the simulation, and then consider the forward Gregory-Newton interpolation formula. Okay, so that's the formula. Then I construct the difference table. Okay, the forward difference table. So I have here k, x sub k, f sub k, k delta f sub k, k delta squared f sub k, k delta cube f sub k, and k delta to the fourth f sub k. So these are the values. Okay, so if we are to, let's see, here we have delta f sub k 0.06356. Okay, we have that. That is delta f sub 0, that for k equals 0. Then we have 0.05902 until we reach 0.05195. Okay, and then until reaching this value, no, negative 0.00012. Okay, until we reach this negative 0.0012. Okay, okay, negative 0.00012. Okay, and then if x is 4.4, okay, the value, so r is computed, no, using the formula for r. Okay, so this is your new variable now. Okay, so instead of using x, we use r. No, we use r instead of using x. So this is our new variable r. Okay, so the value of the variable is 0.8. No? So in that case, this was now obtained. So this is applying the forward Gregory-Newton interpolation formula. So we arrived with this answer. Okay, so this is 1.638636. So if we will take a look at the final answer, that is considering 5 decimal places, 1.63864, 1.63836. Okay, so we can round it, no? Round to 5 decimal places. Okay, we can round it to 5 decimal places to have 1.63864. No? So, which is the same as our answer here. Okay, 1.63864. Nagra-round off kasi tayo dito, di ba? Nagra-round off. So, possible na may konting pagkakaiba sa Excel. Okay? Pero okay lang yan kahit may konting pagkakaiba. Basta importante tama yung solution. Okay? So, in this case, we now proceed. So, as you notice, meron dito FACT for factorial. So, halimbawa, factorial 3. Okay? So, yun yan, 3 factorial. 6. Ay, ano nangyari? Ayun, 6. Okay? So, yung gamit ng factorial sa Excel. Yan, FACT ang ginagamit na. Ayan. So, yan ang gagawin nyo, class. So, I hope you understand. So, good day, everyone.